In calculus, we often find the area under a curve. But what happens when the function shoots off to infinity at one of the boundaries? Today, we will learn how to evaluate these improper integrals using limits. An improper integral of the second type occurs when the function is not defined at one of the endpoints. If the function grows without bound as we approach the, we cannot use the standard fundamental theorem of calculus directly. To solve this, we replace the problematic boundary with a variable's t. We calculate the integral over the interval from t to b, and then observe what happens to that value as t gets closer and closer to a. Similarly, if the discontinuity is at the upper limit b, we take the limit as t approaches b from the left. We are essentially calculating the area of a slightly smaller region and expanding it to fill the gap. If the limit results in a specific real number, we say the integral converges. However, if the limit results in infinity or does not exist, the area is infinite, and we say the integral diverges. Visualize a sliding door at t. As t slides toward the vertical asymptote, the area accumulates. If that accumulation levels off at a specific number, we have successfully found the improper integral's value. Let's work through an example. The function 1 over the cube root of x is undefined at 0. We set up our limit as t approaches 0 from the positive side, replacing the 0 in our integral. Using the power rule, the antiderivative of x to the negative 1/3 is 3/2 times x to the 2/3. We then evaluate this at our boundaries, 1 and our variables t. Finally, we take the limit as t goes to 0. Since 0 to the 2/3 power is 0, the second term vanishes. The integral converges to 1.5, which is the total area of this infinite region. Now let's look at 1 over x. We set up the same limit process. While this curve looks similar to the previous one, its rate of growth toward the y-axis is much faster, which changes the outcome. The antiderivative is the natural log of x. Evaluating at the boundaries gives us the natural log of 1, which is 0, minus the natural log of t. As t approaches 0, the natural log drops toward negative infinity. Because the limit is infinity, the area is not finite. We conclude that the integral of 1 over x from 0 to 1 diverges. This illustrates that not all improper integrals have a solvable area. If a discontinuity occurs in the middle of the interval, you must split the integral into two separate improper integrals. Both parts must converge for the entire original integral to be considered convergent. To summarize, always check your boundaries for discontinuities first. Replace the problem point with a limit, perform your standard integration, and then evaluate the behavior of the result as it approaches the limit. Let's test your knowledge. In this integral, where is the discontinuity? If you chose x equals 4, you are correct. To solve this, you would take the limit as t approaches from the left. Mastering improper integrals allows us to explore the boundaries of infinity in geometry and physics. Keep practicing these limit setups to ensure accuracy. Thank you for watching. Generated by Vision Solve AI.